Okay, so you noticed on that quiz that you had at least one Hoffman question and one Zaitsev question. So anyway, there was on there, and we'll talk about that in the review. I have the review right here, so we're going to get to that too. So let's finish on what we were talking about before about chapter 7. Okay, we were learning, the last thing we learned was that when we had cyclohexane, you had to have your leading group in an axial position with an available axial hydrogen to make that product. So you always want to rearrange your chair from chair 1 to chair 2 so that you have your halogen in the axial position and a hydrogen available also in an axial position, at least one carbon away in a beta carbon. So now we're going to switch gears a little bit and tell you why the conjugated system does not follow Zaitsev's rule, okay? And it has to do with the stability of the intermediates, okay? So when we see a compound where we have 2 halogens, and in this case, it's they're 2 carbons, they're 1 carbon apart, so it's like a 1, 3, or in this case, it's actually a 1, 2, 3, 4, 5, 3, 5 dichloro compound here. When we remove the first proton from here or here, it's going to remove it from here, right? Because this is the tertiary site. It's going to give us the most stable alkene. So when we remove our first one, it's going to give us that most stable alkene, our tri-substituted alkene. Okay, so we expected that. That follows Zaitsev's rule. Okay, but when we try to remove this one, we don't get the more substituted product. We end up with the conjugated product instead. Okay, so there's a reason for this. Okay, and if we look at the mechanism here, we can look at which atom is going to be formed. So in this case here, the first one that we can remove is this one and this one, giving us our alkene. And so that's going to give us this portion here. Now we have 2 choices, okay? We have the choice with the blue arrows here, where we can give it away as give it the most substituted, or we can do with the red arrows here and do the one in conjugation, okay? So the reason we go for that is that this is now an allylic position. This is allylic. This is more acidic hydrogen than this, and therefore it's going to go into that conjugation state to give us the less substituted but more stable, because these are in conjugation where these are not. Okay, so let me, so on here. So we're going to remove this first. It doesn't matter. That's going to give us this side of it here. And then if we use the red arrows, we'll get this product here. And if we use the blue arrows, we get this product here. This is more stable because of that conjugation, okay? So, and it has everything to do with the idea that this is an allylic hydrogen. This allylic hydrogen is more acidic and therefore is going to give us the conjugated product. Okay, remember that those allylic halides react really fast. They react faster than the tertiaries or primaries in alkyl halides because of that allylic position. Okay, so now we've made alkenes. We know how to make alkenes, and we know the rules that their alkenes are going to follow. They're going to follow either the conjugation rule. If you already have a double bond, they're going to follow Zaitsev's rule. If you have a small base, and they're going to follow Hoffman's rule if you have a big base. Okay, so those are the 3 that we want to do. But how do we make alkynes, a triple bond? Okay, well, we do the exact same thing, we just do it twice. Now we have 2 choices on how to do this. The first one is where both of the halogens are on the same carbon. And when both halogens are on the same carbon, we call this a geminal, Gemini meaning twin, a geminal dihalide, okay? And that geminal dihalide, the only thing that you need to turn this into a alkyne is you have to have at least 2 hydrogens on that beta carbon. So you can take one of the hydrogens with one of the bromines and the other hydrogen with the other. Okay, but we have to use a very strong base for this. The first one goes pretty easily with just hydroxide or alkoxide. However, the second one is a vinylic bromide. Okay, remember, vinylic bromides do not undergo substitution reactions. Okay, but we need a much stronger base to get this vinylic hydrogen and this vinylic bromide to leave to give us our alkyne. So we use sodium amide. This is amide, nitrogen -1 with 2 hydrogens on it, okay? Now, it is such a strong base that it doesn't even act as a nucleophile, okay? It is such a strong base, it doesn't even act as a nucleophile. And so when we have these geminal dibromides here, we're gonna take off one from one side, create a vinyl bromide, which can't undergo substitution at all. And then we're gonna remove that second equivalent of HBr to give us our alkyne. Now, what if you have one carbon on the alpha, one chlorine on the alpha carbon and one on the beta carbon? Well, we call this vicinal, meaning nearby, related, nearby. And so we have one on one side on the other, and we're going to do the exact same thing. One of them is going to be first, giving us our vinyl, in this case, chloride. And then we're going to have to remove the second one again with this very strong base, sodium amide. So you must use sodium amide in to form your alkynes here. Okay. So think about that. If you see something with 2 halogens and a sodium amide, it's trying to make an alkyne. Okay. Questions on that? All right. So let's review the E2 mechanism. Okay, the E2 mechanism is analogous to the SN2 mechanism. It happens all at one step, right? We have the base coming in and reacting with the substrate, and therefore it's a second order reaction, okay? It happens in that one step, and tertiaries go faster than secondaries that go faster than primaries, okay? All right, and it's favored by strong bases. Now, which way the double bond goes depends on what the size of base you have, okay? Because big bulky bases also do E2, okay? They just take a different hydrogen, okay? The better the leading group, the faster the reaction. So iodine is better than bromine, which is better than chlorine, okay? And it's favored in polar aprotic solvents. Okay, think about that. Polar protic solvents promote carbocations. Do we form a carbocation in this reaction? No. Therefore, in a polar aprotic solvent, it will go faster. Okay, so questions on that. So that's all of E2. So we have SN1, SN2, E1, E2. I've uploaded that blank chart to Canvas so that you can go and practice filling out that chart and rationalizing where each of those things go. And once you work through that a couple times, you're gonna start to see, oh, that makes sense because this, and then you'll have a really good idea about what your products are. And then you're gonna look at that and say, oh, how do I use that on the exam? It's like, okay, all right, I have a secondary alkyl halide. Okay, what's my solvent? Okay, what's my nucleophile? Is it hot? Okay, think of those questions, and then you're gonna, with that information, you should know exactly what type of reaction is gonna happen. Then you just need to know how to draw the correct product or pick the correct product out of the suggested ideas. All right, questions on that? All right, you have a little more stuff to do with alkynes and reductions. So we're gonna finish off this chapter pretty quickly. Okay, so when we look at the E1 reaction, we form a carbocation. Okay, so that's the first thing that happens, and then the base comes in and removes a hydrogen. So in that case, we probably need to think about the regioselectivity of this. And it turns out, because the more substituted alkene is more stable, we typically follow Zaitsev's rule. Okay, we don't have a competition now between the bigger base or the littler base, because we've already formed the carbocation. Okay, and so when we already formed the carbocation, we typically follow Zaitsev's rule, giving the more substituted alkene as our major product. You still get both products, but the major product is your more substituted, more stable alkene. Okay, and like in an SN1 reaction, iodine is a bigger, longer bond, and therefore it reacts faster. It's easier to take that off and form that carbocation. So iodine reacts faster than bromine, reacts faster than chlorine, and chlorine is very hard to do. Okay, so we're following that same thing. The biggest, longest, weakest bond is easiest to break. Therefore, it's the fastest in our E1 reaction because that's the first step, the slow step, the rate limiting step. Okay. So when we look at E1 reactions, we're going to see that the tertiaries and secondaries are going to be the ones to react in E1. They're going to form that carbocation and the base is going to react with that. Okay. So we're going to see very little of the methyl or primary in there, and the 2s are going to go pretty slow. Okay. But what's the other problem with forming that carbocation? It's always in competition with SN1. So you're always going to get a substitution product and an elimination product. You can force it to elimination products by heating it up. You can force it to do some more substitution products by cooling it down. But you're always in competition. That's why the tertiaries are always the more reactive, because they make the most stable carbocation. Okay. So is it easy to pick your products from an E1 reaction? Not necessarily, because it forms a carbocation. What do carbocations do? They rearrange if they can. So if you have a secondary alkyl halide, you need to start looking for that tertiary carbocation. Where can that tertiary carbocation go with a 1,2 methyl shift, a 1,2 hydride shift, or a ring expansion? So you have to look for those things when you have that. So you always have the possibility of doing a rearrangement. And in this case here, we have a secondary carbocation, and it's actually going to rearrange to give us an allylic cation. The allylic cation, even though it's secondary, is more stable. Remember, the allylic cation and the benzylic cations are more stable than the tertiary carbocation. So it did move to a more stable position. Okay, so in this case here, we had a secondary carbocation, and then it's going to move over one slot here by a hydride shift to give us our allylic. And our allylic is even more stable than tertiary. So that's why it moved. And that means when it does our final removal, we actually will end up with this conjugated diamond. Okay, now we can do that same thing in the case of benzene, right? Because benzene is one of those things that gives you a benzylic cation, and the benzylic site, which is right here, is going to be more stable than a tertiary site as well. So what's going to happen is we're going to form our secondary carbocation, and we're going to do a 1,2 methyl shift to get to that. Not only is it tertiary, but it's also benzylic. It is like probably the happiest carbocation in the world. You know, it's got everything it needs. It's got overlap with the benzene ring, plus it's tertiary. And then when we close that ring, when we remove this hydrogen here, we end up with our nice tetra-substituted compound. Notice if it didn't move, it would actually only give us a tri-substituted. Actually, it would only give us a mono-substituted because it'd have to be over here. But by moving to that benzylic site with a 1,2 methyl shift, it gets to that benzylic cation, which is one of those happier cations, and we ended up with the tetra-substituted product. All right, questions on that? Okay, so when we're looking for this stereoselectivity in these E2 reactions, we have to remember what the shape of that carbocation is, right? That shape of the carbocation, it's trigonal planar, and that orbital is empty above and below that plane. And that orbital is most likely already hyperconjugating to one of the sigma bonds between carbon and hydrogen on an adjacent carbon. That's going to allow it to have that nice stability and be in that fast reaction once you form the carbocation. Okay, so the slow step is forming the carbocation, then the fast step is losing that proton to whatever base is available to make your double bond. Okay, so in this case, because we're looking at a trigonal planar system, we get the E isomer as the major product. What does E mean? Opposite, right? So it's the opposite one. So you're wanting those groups to be in the outward position. Now, because it's trigonal planar, it's going to give you where you're going to have a group here, and then one of the groups is going to be here, here, and they're going to be opposite each other because of sterics. So it'll twist around and have that hyperconjugation. So those big groups are far apart as possible. So if we look at the product down here, we have a nice beta carbon right here with one hydrogen on it. And that's going to give us probably our major product, because that's going to be giving us a really substituted alkene. Okay, so we're going to make our carbocation. And so when we make our carbocation, this big group is going to try to stay away from this big group here when we form our double bond. And therefore, we end up with our E as the major product. You do get some of this, but this, your E is the major isomer. Okay. And it's all because that trigonal planar structure wants to have that pi either on either side, and so it can take the hydrogen to make it happen. Okay. So let's look at E reactions on cyclohexane. Okay. So before I said, when you do an E2 reaction, you have to have your halogen in the axial position, and a hydrogen has to be in the axial position to get the reaction to happen, because it's a concerted reaction. That requirement no longer exists, because you're going to form a carbocation and you're going to make it a trigonal planar structure. And so what you're going to actually do is, once you lose this chlorine right here, this is actually going to flatten out. So that means any hydrogen that's beta is going to work. So you want to follow Zaitsev's rule here and say, okay, I have a hydrogen on a substituted carbon, which is going to give me the most substituted alkene. And so, well, you have hydrogens here and they are in the axial position. You actually are going to take away the one giving you the more substituted alkene. Okay. So the more substituted alkene works in here because you're not limited by the configuration. Remember when we were drawing the Newman projections and you had to have those two anti to each other, that requirement goes out of the way when you form the carbocation. Okay, but don't forget about rearrangements. Okay, in this case here, we had the bromine over here on a secondary carbon. And when we form the carbocation, it's going to do a 1,2 hydride shift to give us our tertiary carbocation. And actually, it turns out it's going to end up giving us the same product that the 2-chloro was giving us. The 1-bromo, I mean, the 3-bromo is going to give us the same thing. So the chloride was here, the bromide is switched over 1, but because of that being able to form a tertiary carbocation, it will, and therefore you can then follow Zaitsev's rule and get the most substituted alkene. All right, questions on that? Okay, so that means that in summary, we have first order kinetics. It only matters what kind of alkyl halide you have. It's in 2 steps. You always form a carbocation. That means tertiaries react faster than secondaries, and primaries hardly react at all. It's favored by weak bases, water and alcohols. So that's polar protic solvent right here. The better the leading group, the faster the reaction, because you have to break that bond first. So iodine's better than bromine and bromine's better than chlorine. Okay. And again, the polar protic solvents are because of that carbocation is stabilized in polar protic solvents. All right. So the E1 is both regio and stereo selective in the fact that what it does, and it is always in competition with the SN1 reaction. Okay. There's usually a rearrangement if it can, so always watch for rearrangements. 1,2 hydride shift, 1,2 methyl shift, and ring expansions. And then the reactions of these reactions are not as useful because you get 2 products. You get competition products. So it's not as useful as an SN2 because you only get 1 product and it's stereo selective as well. Okay, so when an E2 reaction the stereoselectivity comes from which hydrogen you remove, right? On the beta carbon, okay? And that hydrogen has to be in a position where it's anti to the leaving group. So that gives rise to mostly E, because that'll give your groups to be in the anti position while your hydrogen and your bromine are in the anti position. But it does give some Z, okay? It's not 100% foolproof. It'll react slower, but sometimes it's going to be in gauche and you will get the Z product, okay? The carbon, the hydrogen removed, bonded to one hydrogen, you will get the anti-elimination, which will also be one. So in the first case, you have two choices for hydrogen, but it'll still try to give you mostly Z. I'm sorry, mostly E, mostly opposite. Mostly opposite. If you have one, it'll try to give you mostly opposite or mostly together. If you only have one choice, whatever position you have to do to put them into the anti position is what you're going to get. So you have to draw that Newman projection, get the leaving group and hydrogen in the anti position, then that tells you, well, you get it. So it's isomer dependent. It's isomer dependent. Okay. So for stereochemistry, SN1 always gives racemization. For SN2 always gets inversion. Okay. So that's a great thing to know when you have there. And in E1 reactions, you do get mostly E because of the carbocation, and it can arrange. In E2, you mostly get Z unless the only way you can get, you have one hydrogen and you have to rotate it so it's anti, and that gives you your Z conformer. So most of the time it'll give your E, but if you only have one hydrogen, you got to look for it, whether you're getting the Z on. All right. So, and again, the mechanisms are different. Obviously, the E2 is much more common and useful because you only get one set of products. You don't get a substitution product. You only get elimination products. It's favored by very strong bases, alkoxides and hydroxides. It occurs in most of these halides. However, it occurs in all of these halides, but tertiary is faster. That's different than SN2. Tertiary is faster, okay? And because the beta hydrogens are further away from that tertiary center. But tertiary is faster than secondary, which is faster than primary. E1, not as useful because the mixture of products. You have to use things like water and ethanol and methanol because we want weak bases. If they were stronger bases, they go E2, okay? And we can't do it with a primary because you can't form the carbocation. And the secondaries are really slow. All right. All right, let's go ahead and take roll, take a break. Here a little bit. Waiting for a follow-up X-ray today. See if this is healing that. It looks like this. A few more people in the live class today. Thank you. You saw the COVID numbers going down too. That's anyway. All right, all the phones are down. Okay, so let's switch gears a little bit. Okay, dehydrohalogenation. That's what we were talking about to get to our alkenes. And the reason it follows directly after SN1 and SN2 is because we used halogens as our leading group there. And so we wanted to start with a dehydrohalogenation to make our alkenes, but that's not the only way to do it. The other way to do it is actually take an alcohol and an acid. Ooh, interesting. So it's an acid catalyzed dehydration. Removing of water is dehydration, right? So in the case of this, we're going to take an acid, we're going to heat up our alcohol, and it's going to boil off water and give us our alkene, okay? So this can happen in like the gas phase in industry, but it can happen in liquids too. Usually it's a very strong acid like sulfuric acid or phosphoric acid. Turns out sulfuric acid is a pretty decent solvent. I actually use it in one of my reactions upstairs, and it's surprisingly good solvent. And so these reactions work pretty well. In the case of primary alcohols, though, it's really hard to remove that group, that protonated alcohol, okay? And it happens to go by an E2 reaction. And I'll show you what turns into the base when we do that in a minute. But when you look at the secondary and tertiary, it's actually easier to do because they go through an E1 mechanism. It protonates the alcohol, it protonates the alcohol, that turns it into the oxonium cation, which leaves as neutral water. So that leaving as neutral water is really easy. And so it's easier to do secondaries than primaries, and tertiaries are even easier because that breaking of that bond is easier to form that cation. Okay, so let's look at the mechanism of the secondary and tertiaries first. So the first thing we're going to do is we're going to protonate our alcohol here by having the electrons from the lone pair of the oxygen reach out and grab that hydrogen, making a new sigma bond. When we do that, we change the formal charge on oxygen to +1, and we now have our neutral water. We're going to use that in a little minute, okay? So now we have the slow step, which is the breaking of this sigma bond here to give us neutral water and our carbocation. Okay, that's our slow step. So that both the secondary and tertiary do this. So they both go through that carbocation, that E1 mechanism. Okay, now once it's removed, our water here is going to act like a base. Hydronium acted like an acid up here, but we're going to use the water to act as a base to regenerate our hydronium ion and eliminate our carbocation, giving us our double bond. Okay, so this is why it's acid catalyzed. We regenerate the acid, the hydronium ion, at the end of the reaction. And the water that we created after protonating the alcohol became our base. Okay, so these are really cool reactions because you just need a drop of acid and a little bit of water in there, and you can get this reaction to continue to go through generating your alkene and more acid, or the same amount of acid. Questions on that? Okay, so basically we're taking an OH, which would be a horrible leaving group by itself. OH minus as a leaving group, never happened. But water as a neutral leaving group is a really good leaving group. So we're using that temporary protonation to make it leave and give us that carbocation. Okay. So primary alcohols are a little different because we can't form that carbocation. So what we're going to do is we're going to do the same thing. We're going to protonate that alcohol first, right here, but this cannot leave by itself, okay? But when we protonate that alcohol, we generate a conjugate base. This conjugate base is actually very close to where the alcohol is protonated and only has to move over to the beta carbon and find a hydrogen to start tugging on. And when it does that, we get our concerted E2 mechanism, and we get our alkene, and we regenerate our alcohol, and we generate an equivalent of water. So it's a little bit different mechanism, but the fact is that when you generate your conjugate base, just like we did in the first reaction with water, our conjugate base is the one that's going to reach out and grab our beta hydrogen, giving us the ability to have that water leave as neutral water. Okay, again, it won't leave as hydroxide. That's a horrible leaving group. It's going to leave as neutral water. Okay, great. Questions on that? So now we have two ways to make alkenes. Okay, so do you think that these are going to follow Zaitsev's rule? They're going to follow the same rule. They're only going to follow Zaitsev's rule. Can we follow Hoffman's rule here? No, we don't have a big bulky base. We're doing a completely different mechanism. So we're going to give the Zaitsev's product or the conjugated product. Zaitsev's product or conjugated product when we do the dehydration of alcohols. Okay. So one of the issues with the primary alcohols is you can actually have a little bit of competition with SN2 because you either have to have the base come in and act as a base on a beta hydrogen, or your base is probably also a nucleophile and can actually displace your neutral water. So there is an opportunity where you can actually have attack by another substrate. In this case, we're using another one of the equivalent alcohols. So in this one, we started with ethanol, right? And we added our drop of acid, okay? And then we protonated our alcohol to make it a good leading group. But now another equivalent of the alcohol can act as a nucleophile, a poor nucleophile, but a nucleophile. And when it does that, it actually gets to this ether derivative that has a protonation on it. And then if it loses the proton, you actually end up with this ether, which is the substitution product. You were looking to make ethylene, and you ended up making diethyl ether. So there is that is a subtle problem with the SN2 reaction. Okay, so that makes the E1 dehydration more reliable. It's going to give you the elimination product and no substitution products. But in this case, we will get substitution products on the E2. So we only have to worry about the E2 on primary alcohols. E1 is the secondary and tertiary alcohol. So that makes it a cleaner product with no side product. Okay. So this is saying that I just said, sorry. Didn't know I had that slide. So this is basically saying you could have that react with a nucleophile. All right. Okay, so we talked about how to create our alkynes by elimination products, right? We talked about how we had geminal dichlorides, they're on the same one, so they're twins. And we have the vicinal where they're right next to each other right here. We need two equivalents of a pretty strong base to get it to go to the alkyne. Most of the time we use sodium amide, but the bromines are good enough leading group to actually get it to go to the okay. So there's another way to do it where if you have a carbonyl compound, you can actually react it with phosphorus trichloride. And what that does is phosphorus is really oxophilic. It really likes oxygen. So what it's going to do is it's going to pull off your oxygens, and it's PCl5, right? So two of the chlorines are going to transfer to the carbon here. This oxygen is going to transfer to the phosphorus and have the freedom green chloride. So this is your byproduct here. And you get your geminal dichloride. And once you get your geminal dichloride, all you have to do is add two equivalents of sodium amide to generate your alkyne. Okay, so it's the same reaction here, except we took one step back and converted this carbonyl compound into a geminal dichloride. And it works in pretty good.
It necessarily has to be phosphorus.
Yes, it has to be phosphorus pentachloride right here. That's the only, there is a way to do it with another reagent, but phosphorus is really oxophilic, really likes to have that oxygen outside. And notice it's PCl5, so it actually has 10 valence electrons. So, okay, so the other thing we can do once we form our acetylene is we can actually turn it into a nucleophile. If there's a hydrogen on your acetylene, that acetylene hydrogen is the most acidic of the alkanes, right, of the hydrocarbons. It has a pKa of 25, okay? So being that it's so acidic, we can pull that off with the sodium amide we use to make the alkyne, and we can then use it as a nucleophile. All we have to do is hit it with, some other thing that was an electrophile, and it will do a substitution. The cool thing about this reaction is it forms a carbon-carbon bond, okay? Your acetylide ion has the electrons on carbon, and when it attacks your electrophile, it gives you a carbon-carbon signal bond. Okay. So you can think of this as a really strong acid-base reaction, actually, right? So, okay. So how can we use this to our advantage? Well, let's try to make, let's say we wanted to extend our chains on our compound we have, and we want to extend it by 2 carbons. Well, the easy way to do it with 2 carbons, you can't just attack it with a primary anion, because those you can, but those are not as acidic and they're much harder to form. These are much easier to form. And we can use it as a nucleophile. And our anion here is going to attack, of course, the backside of our methyl group here and kick out the chlorine. And notice we've added 1 carbon to this chain. Okay, so we've added 1 carbon to it. What if we wanted to add 2 carbons? Well, we don't use methyl iodide, we use ethyl bromide. And if we use ethyl bromide, we can add 2 carbons. And if we used propyl bromide, we'd add 3 carbons. So you can add as many carbons as you want based on the alkyl halide you use here. Okay, so in this case here, you formed this 1 bond, okay? Can you add more carbon-carbon bonds to this? Well, it still has a hydrogen on the acetylene, so you can actually deprotonate the other side and react it with something else. So you could take this and say, you know, okay, I'm going to take this, deprotonate it again, and put 2 on the opposite side. So we end up with a total of 5 carbons here. Okay, so we actually can take one side, react it 1 equivalent of base, substitute. Take the other side, react with another equivalent of base, put in your next substrate, and you can have any number of carbons you want. So you can have odd numbers or even numbers of carbons. You just have to choose your substrate correct. Okay. And the problem is that, okay, the pKa was 25, right? And that's a very weak acid. So that makes it a very strong base. So one side reaction you can have with secondaries and tertiaries is you're going to get elimination products. It's going to act as a base. So you can get these substitution products on primaries, primary alkyl halides, but when you get secondary and tertiary, now you start getting elimination, especially because the tertiary is not going to do substitution, but we have our acetylene going and attacking the beta hydrogens and giving us our elimination products. Okay, so we're going to use this reaction with acetylide ion to extend carbon chains a lot, all this semester and next semester. So that's one reaction you might want to look at. In fact, next week after our exam, we're going to start our reaction tables. So we'll see how that goes. Okay, so let's see. The next thing we want to do is we want to, how do alkenes react, right? Let's figure out how alkenes react. So the one thing that we can do with alkenes is we can reduce them back down to alkanes. And we do this with what we call catalytic hydrogenation, okay? So hydrogen itself has a nonpolar bond. That bond's not active enough to go and add across that alkene. So what we have to do is we have to use a metal catalyst. And so what happens is our hydrogen adsorbs to the metal catalyst and reacts with the metal catalyst. Now we have a metal hydrogen bond. Now that's a very reactive bond. And now when our alkene comes down and sits on top of it, it can transfer 2 hydrogens to that system. Okay, so let's look at, see what that has in here. Most of the time we use palladium, platinum, or nickel. Usually it's kind of divided onto a substrate so you can just filter it out of the reaction. But it can be used, any of those will work. Now, in this case here, we're doing an addition reaction. So we're going to split this hydrogen, going to put 1 here and give us our saturated hydrocarbon. Okay. Now, we can't really tell how they added. Did they add on the same side or did they add on opposite sides? And so this is a selectivity issue that we're going to have to start talking about in these reactions with alkenes. Okay. Did it add at the same time or did it add from opposite sides? Okay. Next chapter, we're going to do a lot of that syn and anti-addition. But what I'm going to tell you now is that our hydrogens, because they're on the surface of the metal, okay, our hydrogens are on the surface of the metal. When our alkene comes down to do it, both hydrogens add from the same side. When both hydrogens add from the same side, we call that syn addition, same side addition, okay? When they add from opposite sides, we're going to call that anti-addition. Okay, so in this case, we're doing what we call a syn addition and hydrogenation. Okay, so in theory, these reactions give off heat, right? That's how we tell stability of things, which ones are more stable and which ones are less stable. So in this case here, the upper reaction should give off more heat than the lower reaction because it was a more substituted alkene. Okay, oh, I do have the mechanism. All right, so here's how the mechanism works. Right here, since hydrogen's so non-reactive because hydrogen-hydrogen bond is nonpolar, we actually break that bond and have these hydrogen metal bonds. Those are polar bonds. And if those are polar bonds, this is the electron deficient side, the hydrogen's electron deficient side. So it is our electrophile. So that means that our alkene is the nucleophile. And our nucleophile gets close to the surface where it can add one of them across each of these orbitals to rehybridize into sp3 hybridized orbitals. And we have our number one, our Syn addition because it's sitting on the surface. And number two, reduces down completely. So all of our high electrons are converted into sigma bonds. Questions on that? Okay. So the kind of rate of catalytic reduction is that the less substituted it is, the faster it goes. Okay, does that make sense? You know, from a sterics point of view, if you have only one group, it's easy to get to sit on top of that surface. If you have two groups, now you got to make sure that both groups are kind of out of place and sitting on that surface. You have three groups, now it's a little further away, and so it's going to react a little slower. And with four groups on it, it's going to be the least reactive. Okay, so it's also least reactive because of mainly because of the crowding, but also because that double bond has less energy. It's less reactive just from that standpoint. Remember, our less substituted gives off more heat. It's less stable. Our less stable thing reacts faster. Okay, so you can look at it both of those ways. So that works for alkenes, and that's great. But what about alkynes? Okay, well, alkynes, it turns out, if you have an alkyne, it'll also react with catalytic hydrogenation. And the first double bond, the first pi bond will go away, and that'll give you an alkene. The problem is you can't stop there because you now have an alkene which already reacts with catalytic hydrogenation. So whenever you use catalytic hydrogenation, it always takes it down to the alkane. It does not stop at the alkene. Okay, so that's a problem if you wanted to stop at the alkene. But we have three reactions that help us stop at the alkene. Okay, so the first reaction we're going to talk about is we're going to talk about Lindlier's catalyst. Okay, and Lindlier's catalyst is basically catalytic hydrogenation, but you poison the catalyst. You make it less reactive. So it's reactive enough to react with the first pi bond, but not reactive enough to dock with the second pi bond. So Lindlier's catalyst, okay? And so it's still catalytic hydrogenation, and it still happens at the metal surface. So we get Syn addition, which means we always get our Z product. We always get our Syn alkene, okay? Because a cis alkene, because it's a Syn addition, happens on the same side. So both of those hydrogens are on the same side, the two R groups go out, okay? So that's pretty cool that we can make selectively our cis alkene using catalytic hydrogenation of an alkyne, okay? But we have to use a special catalyst. It's called Lindlier's catalyst. And you want to use that to make those cis alkenes. But what if you wanted to make the trans alkene? We have a different reaction for that. We have what we call the dissolving metal reaction. In the dissolving metal reaction, we actually have sodium metal. Sometimes you can use lithium metal too. We're having ammonia as a solvent here. It's also going to turn out to be the proton source. Okay? And we're going to have our alkene. And so what's going to happen is we're going to actually do single electron transfer with the sodium going from sodium 0 to sodium +1. And when we do that, we end up with our trans alkene in our anti-configuration. Okay. So, but the mechanism is different. The mechanism for the cis alkene is the same as catalytic hydrogenation. Comes down on the surface. Okay. The mechanism for this anti addition is completely different. and goes through some anions. Okay. So let's talk a little bit more about that Lindlier's catalyst. Most of the time you take a platinum catalyst and pollute it with lead. So if you see platinum and lead in a system, or you can also do nickel boride, Ni2B, okay? Both of these are less reactive than just palladium or platinum or nickel, okay? But it's still on that catalyst surface, and therefore it still gives you that Syn addition. Okay. But in the dissolving metal reduction, we actually have a very long mechanism on this one. So the first thing that happens is you have your neutral metal. It has one electron in its outer shell. We can use sodium or lithium right here, one electron in its outer shell. So it donates that one electron to the pi group, to the pi orbitals here. And what you end up with is a radical anion, okay? It only donated one electron. Notice there's one barb on this arrow here. It donated one electron. And so there's one electron in this p orbital and two electrons in this p orbital, okay? We're still sp3 hybridized. We still have, we're now sp2 hybridized, and we still have a double bond there. We were sp hybridized, and now that's where these two p orbitals are coming from. They are hybridized orbitals. One has one electron in it, one has two electrons in it. Okay, so we have that. Now those ones with the two electrons in it, that's now basic or nucleophilic. And so in this case, it's going to act as a base and make a new bond with hydrogen to give us a sigma bond here. And we're left with just the radical. Okay. So notice that when we do this hybridization, the orbitals are opposite each other. Our sp3 orbitals are opposite to each other, not because the orbitals are big, but because the two groups need to be trans to each other because they want to be as far apart as possible. So when they form this, it was linear. And when you formed your radical anion, they went to this trans configuration. Okay. Now you use another equivalent of that neutral metal, transfer one electron to there to give us another anion. So now that we have another anion, it's going to act as a base and pull a hydrogen off your ammonia, giving us our addition. So this is why we get our trans alkene, because the first intermediate we get is our trans radical anion. Okay, transferring that one, going from the sp to the sp2 turns it into a trans radical with two p orbitals with electrons in them. And then we transfer one hydrogen, transfer another electron, and then that other hydrogen. So you always get this trans alkene. So you need to know how to do alkanes, alkynes all the way down to alkanes, and that's just palladium on hydrogen, hydrogen on palladium. And you need to know how to do cis alkenes, that's Lindlier's catalyst. And you need to know trans alkenes, dissolving metals, sodium or lithium with ammonia. Okay. All right, questions on that? Okay. I'm actually going to put this synthetic example next week. I want to do the review. Okay, so here's the review. All right, so for chapter 5, stereochemistry, but you need to be able to do RS and priority rules. Okay, it'll also help you with the NZ. So there you go. You need to know how to do stereo, Newman, and Fisher projections. There'll be at least one of each on the quiz, on the exam. You need to know those 3 types of projections. Definition of enantiomers, diastereomers, and meso.
Is it stereo Newman?
Stereo, which is the wedges, Newman, which is the brown one, and Fisher is the one with the vertical and horizontal lines. Okay. Definitions of chiral and achiral. And racemic mixtures and rotation of light. So what I mean by that is if it rotates light 100% this way and you have the other isomer, what's going to happen? It's going to rotate it 100% the opposite direction. And if we have a mixture of them, it has no rotation at all. Okay. So in chapter 6, we're going to focus with the SN1, SN2 stuff. And know how to name your alkyl halides. Nomenclature will still be on here, as well as nomenclature for alkenes, including dienes. So review your nomenclature for alkenes and alkynes, which we did on the last exam, but we're doing it again. Know the definition of nucleophile and electrophile. Okay, be able to recognize your nucleophiles and electrophiles quickly. Bases and leaving groups. Remember, you have different types of bases. You have strong bases, you have small bases, you have bases that can act like nucleophile. Okay. Your SN1 and SN2 rate laws, mechanisms, and reaction diagrams. Know your polar protic and polar aprotic solvents. You know, we had a whole series of DMAC, DMSO, and THF, and acetone. Those are all our polar aprotics, or some of our polar aprotics. Know the difference between endothermic and exothermic. Know stereochemistry difference between SN1 and SN2. SN1 is racemic, SN2 is inversion. Carbocation shape and stability. Carbocation rearrangements. We have 3 types. 1,2 hydride shift, 1,2 methyl shift, ring expansion. Solvent effects. Carbocations are supported by polar protic solvents. Functional groups that can be made with different nucleophiles. Okay, that was that last slide on chapter 6. All right, chapter 7, know E and Z. We now have E and Z plus cis and trans. The alkene stability trans. More substituted, more stable, less substituted, less stable. And we proved that by heats of hydrogenation. Okay, know the rate laws for E1 and E2. They should be analogous to the rate laws for SN1 and SN2. Know their mechanism and diagram too. Regiochemistry. That's the laws. That's the conjugation law, the Hoffman's rule, and Zaitsev's rule. I guess they're rules. Sorry. So those know that identifies where you're going to make your double bond. Be able to identify beta hydrogen. When you're doing eliminations, make sure that you can draw your beta hydrogen anti to your leaving group so that you can get the correct stereochemistry of your double bond. Know the difference between dehydrohalogenation versus dehydration. They're different mechanisms. One uses base, one uses acid. Okay. Zaitsev's rule and Hoffman's rule and conjugation rule. Compare and contrast the SN1, SN2, E1, E2. That's that table. Practice that table right there. Also know the nature of your nucleophile. What is a good nucleophile? Be able to recognize a good nucleophile and a bad nucleophile. Be able to recognize a small base and a good base. Be able to recognize hot and cold. Elimination versus substitution. Okay. The speed at which reactions go based on substrate. You know, SN1, E2s all go faster with tertiary substrates. The nature of the solvent, polar aprotic and polar aprotic and polar protic. The alkyne synthesis, that's the sodium amide to make alkynes with geminal dihalides and vicinal dihalides. Okay, using acetylene as a nucleophile. If there's an acidic hydrogen on there, you can use it as a nucleophile. If it's an internal alkyne, you're done. But if you have a hydrogen there, you can use it. Geminal versus vicinal dihalides, and then reductions. We have 3 types of reductions. Okay, we can take alkynes and alkenes down to alkanes with catalytic hydrogenation, palladium, platinum, and nickel. Okay, if you want to stop at an alkene, you have to use the special reagents of lead or nickel boride, right? That is called, what is it called? I just said it. Lindlier's catalyst. Thank you. Man, I'm old. Anyway, so and then know how to get the transalkene. So The Lindlier's catalyst gives you the cis alkene because it's still catalytic hydrogenation. It's just bad catalyst. You can, to get the trans alkene, you have to use lithium or sodium in ammonia. And it always gives you the trans alkene. Okay. And that is everything on my sheet. This is available online. And so you can look at that too. Yeah. This is available online under resources. It's a chapter 5 through 7 exam review. Okay. So, all right. That's right about time. Anybody have any questions? Okay. Okay, if the natural average of the class is 75 or above, I will wear a kilt to lecture in. I keep threatening you, and some of you just keep trying to do bad on the exam. So, all right. Yes. Yeah, I had. I almost had one last time. Okay, I'm going to stop sharing. I'm going